Today I'll be presenting Are You Excited? IR examination of rotational and vibrational states. So, are you excited? Well, even if you aren't, these molecules are. So, as I'm sure you know, molecules aren't stationary objects. They move all the time. Specifically, diatomic molecules vibrate like that and rotate like this. These types of motion create different energy levels that the molecule can transition between. Vibration specifically is like a spring stretching or constraining, with atoms moving farther and closer together. In classical mechanics, this was characterized by the harmonic oscillator. However, the harmonic potential fails to explain how chemical bonds break, so it was later replaced by the Morse potential. Both of these can be seen here in this diagram. An important thing to note is that the energy levels are spaced equally in the harmonic oscillator, while they get closer together as the vibrational state increases in the Morse potential. Rotational motion, on the other hand, is described as a rigid rotor often. This is where the molecules rotate around each other at a fixed distance. However, these types of motion are not independent of each other. They cause changes in the other. Specifically, the rotational constant is dependent on the molecule's bond length. So as the molecule vibrates and causes the atoms to get closer together and farther apart, the energy required to rotate that molecule at a certain speed will change. IR spectroscopy allows us to study these different levels. IR spectroscopy will cause the molecules to transition between rotational and vibrational quantum levels. Specifically, the only transitions that are allowed will be when both the vibrational and rotational quantum number change by only one integer. So the big picture of this experiment is to compare how isotopes affect constants and energy levels. We'll be comparing DCl and HCl to see what the differences are. How does one more proton change these? And why does that matter to us as scientists? So the research question then is, what does the rotational and vibrational absorption spectra of gaseous HCl and DCl look like? What are the molecular constants corresponding to these transitions? First hypothesis is that the transition from V equals 0 to V equals 2, a change of 2 integer values, will be observable despite being forbidden by the harmonic oscillator selection rules, because the anharmonicity of the Morse potential model weakly allows this transition. The second hypothesis is that the peaks for DCl will be closer together than the peaks for HCl, because the heavier isotope will result in a smaller rotational constant. So the methods used to conduct this experiment that I want to highlight are to establish a vacuum without leaks. So this vacuum line setup was used to establish a vacuum with liquid nitrogen aiding in that process. So the vacuum pump was turned on, and the IR cell, seen here, and the reaction flask, seen here, were attached to this line and checked separately for leaks by closing and opening these manifold valves. Once the leaks were resolved, the sample was ready to be synthesized. So potassium chloride was added to this reaction flask, and sulfuric acid and deuterium sulfuric acid were added to this dropping funnel. The acid was slowly released into the reaction flask, creating gaseous HCl and DCl that went into the line and collected in the IR cell. Once a sufficient pressure was found, the IR cell was removed and a spectra was recorded. The spectra was recorded using an IR spectrometer, which uses IR photons, photons of light in the IR or near IR spectrum to excite the sample between rotational and vibrational energy levels. The detector detects these changes in energy and records them using Fourier transformation. So this is the spectra that we obtained from our experiment. Here you can see the HCl fundamental transition, which was very intense. And then here you can see the DCl fundamental transition, which was less intense. And then in this region, you can see that there are no overtone peaks, although there should be. So this data was obtained from our lab instructor in order to complete the different analysis. So the fundamental transitions are given a close-up here with the R and P branch, which correspond to an increase in the vibrational quantum level and a decrease. And then once again, you can see the more intense peaks in the HCl, less intense in the DCl. And you can also see that the HCl peaks are a bit farther apart than the DCl peaks. This is once again true here, where the HCl are farther apart and the DCl are closer together, but the peaks are both pretty intense, similar intensities in these overtone transitions. Next, curve fitting was used for analysis. So this was done by taking the transition energy values for both the fundamental and overtone transitions and the P and R branches separately, and then plotting these against the initial J value of the transition. Then a polynomial fit was applied to the graph, and these equations correspond to the equations below, which will allow us to later find these different constant values. This was also done for DCl, as you can see. And if you look at all of these different graphs, you can see that the R squared values are all one except for this DCl overtone R branch, which still has a very high R squared value, meaning that all of this data was relatively accurate and precise. Then the constants needed to be determined. So as I said, the polynomial fit equations were used to find average values for BE, alpha E, and D. This equation was rearranged to find RE by using the reduced masses for HCl and DCl. The intercept values were from the different graphs were used to find the fundamental. From the fundamental and overtone graphs were used to find VE and VEXE. And then this equation was used along with the reduced mass to find K, the force constant, and then DE, the depth of the Morse potential, was found using this equation. And then DO, which is the bond enthalpy, was found from DE and those other constants. DO is just at the ground state energy level, where DE is all the way down to the bottom of the graph. So these are the resulting constants. As you can see, they are all slightly different than one another between HCl and DCl. Specifically, BE is smaller for DCl as predicted. And therefore, most of the other values for DCl are smaller. So the conclusions that I want to point out one last time are that the energy levels are spaced farther apart in HCl than in DCl. This could be seen on the spectra, looking at the close-ups of the different peaks. It could also be seen in looking at the constants, where all the DCl constants, except for D, which is very small compared to the other constants, is small. These values are smaller in DCl. So this conclusion brings up an interesting question to me. Is this true for other molecules? Will hydrogen always create energy levels that are farther apart than deuterium? One way to study this would be to compare H2 and D2. I'm interested to see how looking at a molecule made up of the same atom differs from looking at a molecule a heteroatomic diatomic molecule. So that would be a next step for this research. And then I also want to point out that the data mostly fits the line transition intensity model with the different peaks having different intensities, the maximum being around the third or fourth energy, the third or fourth peak. This would not be true, though, at higher temperatures. A higher temperature would cause more intense transitions to be observed at higher J values. And then finally, a shortcoming I want to point out is RE and alpha E were dependent on isotope despite the assumptions made in predicting energy levels, saying that they should not be, that they should be the same between HCl and DCl. This was not what we found. So this could be further investigated. And then lastly, I still want to point out that the fundamental and overtone data were from different samples, so this may have caused various inconsistencies in the data. That is all for me, so thank you all for watching my video. Bye.